Right now, two human-built machines are drifting through interstellar space. Most people only know one of them, Voyager 1, the farthest object our species has ever launched, famous for its golden record and for being the first craft to leave the solar system's protective bubble back in 2012. But a second probe is out there too, moving in a completely different direction through a completely different slice of interstellar territory. That probe is Voyager 2, and this year it may become the most important spacecraft in the entire mission. Not just for what it has already discovered, but for what engineers at NASA are about to try on it. Voyager 2 carries something Voyager 1 lost decades before it ever reached the edge of the solar system, a working plasma sensor. That single piece of surviving hardware turned out to be the key to understanding the boundary where our sun's influence ends and the galaxy begins. When Voyager 2 finally crossed that boundary, its readings didn't simply confirm what Voyager 1 had already shown scientists. In several important ways, they complicated the picture, raising questions that the first spacecraft, for all its historic achievements, was never equipped to answer. And now, in mid-2026, NASA's engineering team is preparing to attempt something that has never been tried before on either Voyager spacecraft: a sweeping, all-at-once overhaul of Voyager 2's remaining power systems, an operation the team has nicknamed the Big Bang. It is a single, irreversible maneuver planned and executed across a communication delay of more than 16 hours in each direction, with no opportunity for a do-over if something fails. If it works, Voyager 2 gains extra operational life, and the outcome will directly shape whether a similar attempt is made on Voyager 1 later this year. To understand why this moment matters so much, it helps to go back to the beginning. Voyager 2 actually launched 16 days before Voyager 1, on August 20th, 1977, even though it carries the second number in its name. That naming reflects the order the two spacecraft were expected to reach their destinations, not the order they lifted off. Voyager 1 was set on a faster, more direct path that would take it past Jupiter and Saturn before angling out of the solar system. Voyager 2 was given a longer, more demanding route, one designed to let it do something no other spacecraft had done before, and which nothing has repeated in the nearly 5 decades since. Voyager 2 remains the only spacecraft ever to visit all 4 of the solar system's giant planets: Jupiter, Saturn, Uranus, and Neptune. Every one of the outer worlds was examined up close: its atmosphere, magnetic environment, and moons studied by instruments built with 1970s technology. Voyager 1, in contrast, swung past Jupiter and Saturn and then turned north and out of the plane of the planets, trading a look at Uranus and Neptune for a closer pass by Saturn's giant moon Titan and a faster route toward the edge of the solar system. That decision came at a cost for Voyager 2: time. Its complicated, multi-planet path meant it took years longer to reach the same kind of boundary Voyager 1 crossed in 2012. Voyager 2 did not cross into interstellar space until November 5th, 2018, more than 6 years after its twin. For all those years, Voyager 1 alone was returning data from beyond the solar system's edge, data that puzzled researchers and forced them to question their models. But the story from Voyager 1 was missing something crucial, something that had broken decades before it ever reached that boundary. And that gap is where Voyager 2's story really begins. Here's a detail about Voyager 1 that rarely gets mentioned when people describe its discoveries at the edge of the solar system. The instrument built to directly measure the plasma around it, its temperature, density, and speed, stopped working in 1980. That failure happened before Voyager 1 had even reached Jupiter's orbit on its outbound journey, more than 3 decades before the spacecraft crossed into interstellar space. By the time Voyager 1 reached that historic boundary in 2012, it had no way to directly sample the plasma on either side of it. Scientists could still study the crossing indirectly, using other instruments such as the cosmic ray detector, the magnetometer, and the plasma wave subsystem. But direct plasma measurement, arguably the single most useful tool for understanding a plasma boundary, was simply unavailable. Researchers were forced to work around a hole in their data that had existed since before many of them had started their careers. Voyager 2 never lost that instrument. When it crossed the same kind of boundary 6 years later, it carried a plasma sensor that had survived since launch and was still returning usable data. That fact alone made its 2018 crossing historically significant. It produced the first ever direct, simultaneous measurement of plasma on both sides of the heliosphere's edge, inside the solar wind and out in true interstellar space, captured in real time as the spacecraft passed through. The scientific community's reaction was immediate. In November 2019, 5 separate research papers appeared together in the journal Nature Astronomy, each describing a different piece of what Voyager 2's instruments had found. Taken together, the findings didn't simply validate 6 years of inference built on Voyager 1's incomplete readings. They overturned some of it. The first surprise concerned the sheer scale of the transition zone. Researchers had generally expected the boundary between the solar wind and interstellar space to be thin and comparatively sharp, spanning perhaps a few 100,000 kilometers. What Voyager 2 detected instead was a broad, roughly 100 million mile wide layer sitting just outside the true boundary. Not inside, where the solar wind still dominates, but out in what should have been undiluted interstellar territory. Instead, the probe found a region where interstellar particles had already pushed inward, like roots working through rock, mixing with the outbound solar material in ways the models never anticipated. Voyager 1 had seen a related but distinct phenomenon on its own approach years earlier, a stagnation region where the outward-moving solar wind slowed nearly to a standstill just before the boundary, as though it had run out of momentum. Voyager 2, arriving from an entirely different direction and crossing at a different point on the boundary, encountered a layer of similar width but with markedly different plasma properties. Two spacecraft, two crossings, 6 years apart, two very different pictures of what is supposed to be the same kind of edge. Adding to the puzzle, mission scientists noted that both spacecraft crossed the boundary at strikingly similar distances from the Sun. Despite crossing at very different points in the 11-year solar activity cycle, when the size of the heliosphere was expected to expand and contract noticeably. One crossing occurred nearer to a period of high solar activity, the other during quieter conditions, yet the boundary sat in nearly the same place both times. Senior researchers on the mission were candid that this result did not fit existing expectations, and that the underlying reason remains genuinely unresolved. The second major surprise to come out of Voyager 2's crossing involved temperature. Solar wind plasma is hot in the technical sense used by physicists. Its particles move at tremendous speeds. Researchers expected a clear temperature drop as that fast-moving plasma gave way to the colder, denser material filling true interstellar space, and they assumed this transition would be one of the defining features of the crossing. What the spacecraft's plasma instrument actually recorded was a temperature drop sharper than anticipated, compressed into a narrower zone than the models predicted. Meanwhile, both spacecraft together confirmed something else. The plasma outside the heliosphere is considerably denser than the plasma inside it, more than 40 times denser at the boundary itself, based on the combined readings. Space between the stars, it turns out, is far from empty. Voyager 2's plasma instrument also delivered the first direct measurement of interstellar plasma temperature, somewhere in the range of 30 to 50,000 degrees Kelvin. That is scorching by everyday standards, but dramatically cooler than the plasma just inside the boundary, which registered in the tens of millions of degrees. Before this measurement, scientists had only been able to estimate interstellar temperature from theoretical models, and it turned out those estimates had been off by roughly a factor of 2. The third, and, according to longtime Voyager project scientist Ed Stone, most remarkable finding concerned the nature of the boundary itself. It is not a clean, sealed wall separating two environments. It leaks, genuinely, physically leaks, with particles crossing in both directions. On its approach, Voyager 1 had detected tendrils of interstellar material pushing inward into the heliosphere. Voyager 2, approaching from the opposite side of the solar system, observed something different but related. A steady trickle of low-energy solar particles escaping outward into interstellar space even before the spacecraft itself had crossed the boundary. Because this leakage was observed from two different approach directions, at two different points in the solar cycle, researchers concluded it wasn't a local quirk. It appears to be a fundamental property of the boundary itself, something no model built before these two crossings had accounted for. Stone described the relationship between the Sun and interstellar space, not as a hard edge, but as something closer to a coastline, with material washing across the interface in both directions like surf between two oceans. Notably, both spacecraft remain, even now, within a turbulent transitional region rather than fully undisturbed interstellar space. Meaning even today, 13 and 16 billion miles from the Sun, they are still sensing the influence of the solar system they left behind. None of this was accidental in its broader design. When mission planners in the 1970s sent Voyager 2 on its longer, 4-planet route, they understood it would cross the boundary later, from a different direction, and provide a second, independent vantage point on the same kind of edge. What they could not have predicted was that the single most valuable instrument for understanding that edge would fail on one spacecraft and endure on the other, turning a planned division of labor into an unplanned windfall of scientific insight decades later. Fast forward to 2026, and the story shifts from discovery to survival. Voyager 2 currently operates 3 functioning science instruments: the plasma sensor responsible for the historic 2018 measurements, a working magnetometer, and an active plasma wave subsystem. Together, these 3 instruments provide something unmatched anywhere else in the history of space exploration: a continuous, real-time, on-site measurement of conditions in interstellar space, gathered by a machine physically present in that environment and moving through it at roughly 34,000 miles per hour. But the resource that makes all of this possible is running out. Both Voyager spacecraft are powered by radioisotope thermoelectric generators fueled by plutonium-238, a material that decays at a steady, entirely predictable rate. Each year, that decay strips away roughly 4 watts of available power from each spacecraft. At launch, each Voyager had about 470 watts to work with. Today, Voyager 2 has slightly more remaining power than its twin, which is why it still runs 3 instruments, while Voyager 1, after shutting down its low-energy charged particle instrument in April 2026, is down to 2. Even so, the margin left on Voyager 2 is thin and shrinking every year. That is the problem the Big Bang procedure is meant to solve. As described by the Jet Propulsion Laboratory engineering team, the plan involves swapping a whole group of powered systems simultaneously, shutting some down, replacing others with lower power alternatives, to keep the spacecraft's remaining instruments warm enough to keep collecting usable data. The name reflects the all-at-once nature of the change. Rather than making one adjustment at a time, verifying it, and moving to the next, the team intends to execute every change in a single coordinated operation. The reasoning behind that approach comes down to risk. Any staged reconfiguration of a spacecraft's power system passes through intermediate states where the system is neither fully in its old configuration nor fully in the new one. Those in-between moments are dangerous because both Voyager spacecraft carry automated fault protection systems designed to shut components down on their own if power draw appears to exceed what the generators can supply. The entire purpose of doing everything at once is to minimize the time spent in those vulnerable transitional states, moving through the changeover as quickly as possible rather than lingering in it. If the procedure succeeds and the new power configuration recovers meaningful headroom, it could extend the working life of Voyager 2's remaining instruments by at least a year, possibly more. And if it goes well on Voyager 2, the same procedure is expected to be attempted on Voyager 1 no earlier than July 2026, with hope that success there might even allow the previously shut down charged particle instrument to be brought back online. Voyager 2 is going first, not because it matters less, but because its slightly larger power margin makes it the safer test case for a maneuver that has never been attempted before, at a distance where every command and every confirmation takes more than 16 hours to travel one way. Keeping Voyager 2's instruments alive isn't just about extending a mission for its own sake. It's about preserving the only active source of certain kinds of knowledge that exists anywhere in human reach. The 5 2019 research papers established that the heliosphere's outer boundary leaks particles in both directions, that it sits at nearly the same distance from the Sun regardless of the solar activity cycle, that interstellar plasma just beyond it is both denser and cooler than expected, and that its structure looks different depending on which direction a spacecraft approaches from. Each of those findings open new questions rather than closing old ones. Why does the boundary hold its position through both high and low points of solar activity? What actually determines where it sits, if not the pressure of the solar wind? What mechanism drives the